Yeah, welcome everybody. Um, this is a double feature this week and next week with the slides that I uploaded. It's about electrode designs, and after I've tortured you with 2 weeks of electrochemistry and physiology and all of those things, my idea is to show you what's around as electrodes. You know, now having a bit an idea why things might look like as they do, this is now more a practical thing today for peripheral nervous system interfaces and next week for central nervous system interfaces. And when I browsed through this morning, I found out that they really look old, and I didn't like that. Therefore, I backed up the old presentation with recent research results and want to share that with you, especially for one reason. First of all, it's always nice to have research and established things somehow balanced. And the other issue is that Elon Musk promised to give a press release on October 30th and then send out another press release that he cannot hold this deadline and will come up on November 31st. No, November 30th. We have no 31st. To say something about his Neuralink in humans. And I think you're much faster than I am on Twitter, on Instagram, on whatever. So, and I thought it's probably good to have that backup about the science before those press releases come, that you're able, with your educated guess, to assess how good that press release is. I mean, it will be awesome with respect from media things, but it's always good to be able to put that in the right context, and therefore I thought I'll share some knowledge, thoughts, latest results with you about that. And with that, I like to start for today. Most things that you need are uploaded now in the Ilias system. I hope you can approach them. If you have no access or things look crappy, please let me know, because my view of the page is different from your view of the page, and I'll try my best. There is an owner's view, but I learned last year that the owner's view is different from your view that you have, so still something to improve if the persons are willing to do so. So, I was part of a team in the year 2005 who published a review that is now 17 years old. It still gets cited, that's the good news, and I still have it here on that page because I think we did quite a good job, and since then there have been, I don't know how many dozens of reviews. The thing I like to draw your attention to is the purpose of a review. And to be honest, the older I grow, the less I know what the purpose of a review is. When I started research, I thought the review is something that I read to get certain knowledge afterwards, and that the persons who write the review already pre-structure what they know. That's the beauty of a review. That you don't have to read 200 papers, but you read one paper and get an idea about the field. And I would say a review is a good review if the authors tell you what their purpose is. Yeah, and I found a lot of reviews over the last years that have no purpose in there. That means people write reviews because they have read a lot of papers. And then it's really hard to get the take-home message out of that. If you read something and people tell you there's something like that, there's something like that, there's something like that, there's something like that, conclusion, there are a lot of interfaces. Yeah? That probably saves you 2 hours of searching the papers, but doesn't help you. Therefore, I like to point your attention to reviews if you're looking for something in your master thesis, for example, that you probably check, do the authors have an opinion about certain aspects? And it's fine that you disagree with that opinion strongly, but then you know what others think about the topic. In our case, we took us a lot of coffee and some bottles of red wine to find out. We like to draw our attention to the question, and I hope this is on the next slide because, where do people implant electrodes? How invasive is that? And what is that good for? What benefit do we have with that? And by that thought, we arranged the interfaces, and I hope that I have that arrangement on one of the next slides. So here also in this course, it's about the area of implantation. Where do interfaces go? How invasive are they? And what selectivity, spatial selectivity do I get? And with that in mind, I like to browse with you through most of the approaches for the peripheral nervous system today and for the central nervous system next week, because the brain is somehow a bit more concentrated on one spot in the skull, while there are so many different spots in the periphery where I can place something. So that is the idea behind that arrangement. We can say after the last years where people said, well, it's not only about muscles and eyes and ears, but also about all the other organs in the body that I might target in bioelectronics medicine, that there is really no place in the body where a person did not come to the idea, I could place something in there. Yeah, but if we go a bit more on a bird's eye perspective, we can say here in without yellow boxes, that's the periphery. And to make it simple, one could say we have either the skin, so we are non-invasive and have surface electrodes there. We go into muscles, so we look in a anatomy textbook and know, well, if I want to open my hand, there are extensor muscles on my lower arm. If I want to close my fingers, there are flexor muscles on the other side on the lower arm. And if I stimulate the extensor muscles, all the fingers stretch. If I stimulate the flexor muscles, all the fingers flex. Yeah, that's one option how one could approach that topic. Not saying anything about side effects like, is it really the case, or what about my wrist angle? Is that stable, or does it flutter around? How long can I do that? Get I tired? So is there fatigue in the muscles? Is this a clever idea? What about control signals? That's then the next level. Yeah, but one could say we approach the muscles. And there are approaches that are good, so that work well. And there are other approaches where it's really hard to get that muscle because there are 3-4 other muscles above that. Especially for the lower limbs, we have a lot of muscles that do not only span one joint, but 2 joints, so the hip and the knees, and therefore there it's really hard to predict what kind of force, what kind of torque do we get there. And then we have in the periphery, the peripheral nerves. And this is just here summarized on one spot. Of course, they are everywhere, and we can go everywhere. And if we think about bioelectronics medicine, there are a lot of approaches over the last years who try to target the autonomic nervous system. So that means we have the vagus nerve or branches of the vagus nerve that can end up, let's say, everywhere. There are quite nice approaches which are not that specific, of course, if you are not very specific with your target. But to take something like earbuds, and stimulate over the earbuds your ear, because there are some terminals of the vagus nerve that can be modulated. That's similar to acupuncture or acupressure, where you have those certain spots. You can also do that electrically. Sometimes that looks a little bit esoteric, but if you go in very detailed textbooks, you find those branches of the nerves and they interact somehow. But if you're just twitching your ear, it's probably less selective than really understanding the pathophysiology, for example, of some autoimmune diseases, and then really targeting that on a more sophisticated level. If we come to the central nervous system, by definition, what belongs to the central nervous system, we have the brain and everything that belongs to the brain. This is in the skull, with a disadvantage that we have to open the skull to access that if we don't stay on the skin, or there are new approaches that go under the skin on the skull. That's a bit invasive, but not that much. We can go to the spinal cord, and we can go to the spinal roots. They belong per definition also to the central nervous system. The beauty of the skull is especially, well, in all applications, that the skull is a bony structure, and you take screws or nails or whatever to anchor something in the skull. That sounds really a bit weird, but is done in many cases. While it's really difficult to anchor something in soft tissue. If you are on a nerve in between muscles and everything moves, it's really a challenge to get things floating on one hand side and anchored on the other side, that they don't travel around the body. And this is a challenge that is quite often underestimated, especially in translational research. If you go from first animal experiments where saying, oh, this is acute, this is a fixed animal, so that means you're doing that intraoperatively somehow. And then you have no clue how to bring this into real world with no cables, no connectors, and fully wirelessly when people move around. And when people move around, you might remember, some of you, about movement artifacts. We have the power supply everywhere, and if I walk around, I have different coupling here, interferences. And what works in a silent environment, if you're just sitting still with a lot of Faraday cage around you, might not work if you walk on the street with a tram, with the electricity and all of those things around. And I strongly believe if we have more electric cars, it will not get better, but even worse with respect to the interference that we have in certain distances, and that we probably now should keep in mind when designing new generations of implants there. So that is the anatomical stuff. And it helps a bit, but it does not really help if we want to say, well, how can we guide a designer through those questions? And that is the result of a lot of coffee and some bottles of wine. The funny thing is that was not so stupid, because I think so, because that graph has been copied several times since then from others, by others. What we thought would it make sense to make a graph where we have the selectivity, and we talk about the spatial selectivity. That means what kind of small area, how small is the area that we can target, and the larger the selectivity, the smaller the area, over the invasiveness. And this is probably not very sharp or very objective, but we thought if we have to open the body and we have to open the nerve, and then we poke something through the nerve, this is probably the most invasive that we can imagine. Or even we cut the nerve and hope that the nerve will grow somewhere, towards our target. That's the most invasive, and that is the highest on the y-axis here. And color coding is white letters into black is CNS, black letters on white is PNS. And in general, I don't want to go into the details too much, is the more invasive you are, the higher the probability to be more selective. Yeah, sounds trivial. Yeah, the closer I am to the target, the better I can hit the target. There are some things here in the peripheral nervous system, epineural, circumneural, epimesial, which I like to tell you what this is, what that means, where the advantages and disadvantages are in the following slides. So then you can go by yourself back, if you like to afterwards, to arrange that into a big picture. So, and you can imagine I cannot start without mentioning the cardiac pacemaker, because that is the thing where all electronic implants started. That cardiac pacemaker started in 1959, not that one, the famous one with hardware store epoxy in a tin can of shoe shine. So there are a lot of urban myths around how this was built and all those things, and I want to skip that here. So we had a cardiac pacemaker, and I'm still happy to show you that very old picture here, because it guides us through a kind of history. In the early days, it was not very obvious that we have to make a hole into a vein and push a cable through the vein into the heart. So people started in the early days also to have bipolar electrodes from the outside of the heart, so opening the rib cage, going to the heart and suturing or poking something in there, and having also kind of mesh-like or grid-like structure that could be placed on the outer surface of the heart muscle. This is something I have not seen in the last years any longer, or in my career. So I started in 90-something, 93, 94, and that was already gone to those days. But I think it's good to keep that in mind, probably for experimental approaches, that the knowledge about that has been around in the early days, and that this was a valid approach to stimulate the heart. Nowadays, in those days, batteries were larger, or you have it still nowadays if we talk about implantable artificial hearts. So if you have a complete heart failure and you need a kind of portable heart-lung machine, then you need huge batteries, huge coils to power that. In regular applications, the things shrunk down very much. So we talk about a package that is shown on the right-hand side next to that patient there, which is about 5 centimeters in diameter, probably between 8 millimeters and 15 millimeters in thickness. And 2/3 out of that are filled by a battery. So 1/3 is about electronics, 2/3 are the battery. And it lasts, depending on the functionality and the disease, between 5 years and 10 years. So that's beautiful, and there's an electrode that is connected to that and goes nowadays over the vein into the heart. We take the vein and not the artery, because the veins are low pressure system and don't have so much pressure. That means it doesn't matter that much that you poke a hole into a tube where fluid goes through. I do not like to comment too much on the electrode shape and site, but I can tell you that a lot of the technology that has been used or is used in cardiac pacemakers is taken by other applications. So all the knowledge about materials, titanium packages, stainless steel or MP35N, cables, platinum iridium electrodes. There's a vast experience from pacemakers where knowledge can be taken off. Unfortunately, pacemaker persons, not the patients, but the developers, the researchers, don't want to belong to neural engineering. that means they say, oh, we're a society on our own and do what you do, we do what we want to do. That means if you look for something, you must sometimes type in cardiac pacemaker to come to the papers that might guide you also through questions, what kind of material should I use for packages? Yeah, this is unfortunately a bit separated in the literature. And that was the early one, and then it comes to the question, what do we have nowadays? And talking about that, I just comes to my mind that I forgot some materials there, but I can comment on them later on. So if we don't want to be invasive, we should go to the surface of the skin. That sounds easy and obvious. And the advantage is that it's non-invasive. That means if you have no idea if you would like to have a system after brainstem stroke or after stroke, you have hemiparesia, one arm is paralyzed, so hemiplegia, and you do not know if how it feels to you to get electrically stimulated, and if you would probably benefit from an implant or whatever, you can start with a non-invasive system. That can be done on, done off every time you want to use it. And this advantage, and it's relatively cheap, so if you, relatively cheap means you need somehow energy supply, so probably solar panels in the worst case to recharge your batteries that you need. But if you are on the surface of the skin, it's really hard to get to deep layers of the muscles. You always get the first one. You remember that slide about stimulation? Yeah, whatever is in the way of the electrical field gets excited, more or less. That means if your target muscle is superficial, you're fine. If your target muscle is very deep, you have a problem. If you're completely paralyzed, you're lucky because you don't feel your pain fibers. If you have an incomplete paralysis and you get stimulated, that sensation might come through. If the benefit is larger than the discomfort, you might use that. If it causes pain, you don't use it. And if it causes pain and your fibers are still connected to the brain, it does make something with your autonomic nervous system. Yeah, if you feel pain, if you are excited, whatever, that changes your blood pressure, that changes your heart rate, your ventilation. It releases whatever neurotransmitters. And that means it really does something with you that probably should not be done. If you have a complete spinal cord injury, then these signals don't come through and you don't have to take care of that. Yeah, so that is a kind of trade-off probably. So it's cheap, probably an advantage. You have not the best resolution. That's for sure a disadvantage, depending on the functionality you want to have. If you're fine with just a cylinder grasp, that might be sufficient while taking an implant if you're fine with a simple system. However, one of the challenges is, and you might know that from your daily experience, if you drink enough or you don't drink enough, it's hot outside or cold outside, you feel different. And part of that is how much you're hydrated. You might have experienced that if you forget drinking while being in the hot summer sun, that you get dizzy and you cannot think any longer very clearly. So that means it makes something with you if you get dehydrated. And that starts very early when it comes to conductivity of the skin or subcutaneous tissue and the muscles. So depending how well you have slept and how much you have drunk, the electrical field is different. And that means if you place some electrodes on your skin today, and you know where they belong, they might have different placement, not a lot, but slightly different placement on the next day. And that is a disadvantage. That means you need a certain knowledge about nerves, muscles, electrical current, to place such a system on a daily basis. And something we should not forget is that people who are using that have certain disabilities. So if you are paralyzed on one side, you have only one hand left. That means if you want to place that on by yourself, it's much more difficult as if you would have two hands. And that is the reason why that lady on the upper right has that kind of funny system. That is a spring-like system, two halves of a shell, and you put your arm in, and when you press a little bit, that shell closes. And you can tailor that to each and every person, and then electrodes push on certain parts of your skin. They're large enough that misplacement can be overcome with that. And with that NES handmaster system, you can open and close your hands in a kind of cylinder grip. That means you can do, for example, holding something while you do the fine motorics with the other hand. If you want to use it quite often, it's beneficial with respect to cleaning, maintenance, whatever, rather to go to metal electrodes, even though we all know that they're not the best ones, but they're more robust, more reliable for both recording and stimulation. In stimulation cases, would be good to have a gel underneath or something wet. And the most old-fashioned things are really stainless steel plates where a wet sponge is around, and then you strap them to the target. That looks really weird, but it works. If you don't take care, and especially in places where people are prone to make do-it-yourself work, there are some persons who don't understand the details of electrical engineering but make their own stimulators. If you go to the internet, you find some pages where you can improve your brain and enhance your capabilities when preparing for exams. And you find a shopping list like an empty tin can and 2 meters of cables and something like this. You might have heard about that direct current stimulation of the brain. You place an electrode here, you place an electrode there, and if you turn on the current, there is some indication that your short-time memory increases. If you have no idea about power loss over DC at impedance changes, you might learn it on the hard way with burns of third order on your skin. Yeah, that could happen. And they took a bit care, some legal authorities, that not every crap is there any longer. But I've also in the rehab phase, there were some, especially in UK, but also in France, it's more fashioned than here. It's bicycling or tricycling, three wheels that you don't fall when you have paralysis. Spinal cord injury, you can place electrodes on your leg, and you can do electrical stimulation supported cycling. That means you can go along over the weekend with your friends on your tricycle. And some persons want to be faster, and they tweaked around things and put a diesel battery in their back and things like that. And they also ended up with burns of third order on their legs because they did not understand what that means to get a power loss over dry electrodes on your legs. And if you have spinal cord injury, you don't feel that because the sensory fibers are also blocked. And that means this is an important thing also from the engineering side, to design those electrodes in a safe manner, to design stimulators in a safe manner, that you don't overcome a certain current and voltage level, so that you can limit the power somehow and take care of that. And you might also get skin irritations, not only due to the power loss and the energy that you apply, but if you don't balance out your charges very well, and one pulse is larger than the other, remember there's something with water and water shift, so that means you change the concentration of H plus ions probably. And part of that skin irritation could be a pH shift under the electrode if you don't take care. So that means we also have to take all those electrochemical considerations into mind when talking about surface electrodes. If we are all safe in the limits with silver chloride, with gel, with everything you can imagine, then we're safe, that's good. We can also use that for training. Yeah, in many cases it's also used for supporting diagnosis. If you don't know, is the person still responding to electrical stimulation or not? So that means, are there some peripheral nerves intact? This would be another story, how to do that, and we'll come to that later in a different context. But that can be done with surface electrodes. If you don't know if the muscle works, there's no necessity to try to implant something if you don't know if it works or not. So always a good starting point, but limited somehow. Epimysial electrodes. If we try to understand that by taking the word apart, it's epi is always on the surface. Yeah, and mesial goes towards the muscle. That means those electrodes are on the surface of the muscle. Every muscle is innervated. So that means the nerve comes, splits up and goes into the muscle. And the part where if you would now take an electrode and look what is a good part, the part where you find the best activation, that means a certain strength at the lowest intensity of stimulation. That is called the motor point. And the motor point is quite often about 1/3 from the end of a muscle. That means if you have no idea where the motor point is, you can just try it out on the surface. And this is really how it's done. Also in implantations, people then take an intraoperative stimulation thing. That is a kind of ball on a handlebar, and then they go over the muscle and say, oh, this looks like a good point. Here's the lowest excitation threshold. I'll fix the electrode there. And those electrodes have been applied around between 1996 and 2000-ish. So don't know if it was 2001, 2, 3, 4, something like that. In patients, this device had FDA approval and CE mark. Unfortunately, the company went into bankruptcy in 2006, so then it was taken from the market again. But those muscle electrodes have been around on the market in hundreds of persons, and they have been sutured on the arms, so on the muscles of the arm in paralyzed persons, C4, C5 level of spinal cord injury. They have shoulder movement, they have still elbow extension and flexion, but can no longer move their hands. And the idea was to take that system, and the question was, how many channels do you need? And they said, well, we need 8 channels. 1 channel for the extensors, 1 channel for the flexors, 2 other channels for thumb up and down, and 2 other channels for thumb left and right somehow. That is 2, 4, 5, 6, 2 are left. And the other 2 channels to stabilize the wrist while grasping. If you try that out, I cannot try that out without any pre-known knowledge. If you have your hand hanging loose here and you're taking it up and you don't take care and let it really loose, you find that the fingers move a little bit. Yeah, they close already a little bit. That would mean, if I take my hand in another position, I would now stimulate the fingers and I'll now actively stabilizing my wrist. If you would stimulate the fingers and do not stabilize your wrist, you might have a movement with that. So if you open, it goes probably over the neutral position. If you close, it shifts a little bit to the left. And that would be extremely annoying if you like to grasp something and you always grasp next to it. Yeah. Therefore, the remaining 2 channels were for stabilization of the system. Control was over the opposite shoulder, so if I would have been implanted on my left-hand side, I would have an old-style mechanical joystick on the right-hand side shoulder. Of course, somebody had to place that because I'm paralyzed in both hands, so I cannot put that thing on. And it was that putting your shoulder backwards opens the hand, putting it forward closes it, and if you lift it, you switch over, and then you could move your thumb by moving your shoulder. So it was one channel that could be switched by a third movement then from one function to the other. That is still the same in most of the hand prostheses. There are high-end ones like Michelangelo hand from Otto Bock or the Touch Bionics hand, which use artificial intelligence signal processing algorithms to detect what you want to do. But in most cases, it's just biceps, triceps. One muscle does one direction, the other muscle does the other direction. And if you co-contract both, that's a kind of unnormal, then you switch from one program to the other, and you have a kind of program control then over different programs. That works also for multiple joint prosthesis. So I tried that out at an orthopedic support company, and was for upper arm amputees. That means if you want to grasp something, you first have to think, what elbow angle do I like to have? So you do first the elbow angle, then you do the wrist rotation, and at the end you grasp. And if you are wrong, you can start from the scratch. That means then you adjust the elbow angle, you adjust the rotation, and afterwards you try to grasp again. So therefore, it's really cool if you have some kind of higher level algorithms that detect the movements. That worked well for the upper arm. I've seen a lot of funny to stupid things there. I was involved in one research project where a partner of us was supposed to develop a glove with a lot of touch sensors that the paralyzed person could then get sensory feedback somehow. They succeeded well, and at the very day they found out that the person was left-handed and they made the glove for the right hand. Bad luck. So, but those things happen. The electrodes, just to come back to some technical numbers, were about 8 to 10, well, 5 millimeters in diameter. They were packaged in silicone rubber, and they were sutured intraoperatively to the muscle surface then. Grasping was one thing, very important for the persons, because if you cannot grasp, you lose independence. You cannot feed yourself, you cannot brush your teeth, you cannot drink. That's really high level of independence, but at least for researchers, the imagination to make a person stand up and walk again is as appealing as grasping, sometimes even more. And therefore, a lot of project proposals were granted between, don't know, 99 and 2000. And a lot of persons worked on that, and from time to time new approaches appear, or old ones are reinvented again. And I was involved in one of those projects around 2000. We had a combination of epimesial and neural electrodes. The neural electrodes for the deep muscles while standing, and the other for the epimesials. If you want to stand, what do we need? We need our butt muscles, the straight ones, that's the gluteus maximus, and the lateral ones, that's the gluteus medius. If we want to walk, we want to lift the leg, that's the quadriceps. So that's for balance. Quadriceps is for movement. Knee angle are the hamstrings. They are the deep ones, and they go over the knee. In German, you have no hamstrings. You take the Latin words. That's the muscle the semimembranosus muscle and the semitendinosus muscles. In English, that's the hamstrings. And then you need, on top of that, you don't want to stumble just because your foot is doing what the foot wants to do. So you need foot stabilization on the ankle with respect to rotation, and you have to lift the foot. And that was peroneal nerve. 8 on the right-hand side, 8 on the left-hand side, or 7, I don't know. Probably I have to count here. You can count on that because one connector is one channel. And you see what a mess that is. Yeah? One electrode, one channel. If you have 16 or 18, that was an implant like that. 12 centimeters by 5 centimeters with all those connectors at the end. And I learned my lessons. Surgeons don't want to talk about the length of cables because they think that it's not important. And we tried our best, but I was too young and not senior enough, and therefore they didn't take me that serious. What you can see in that hardly on that screen on the X-ray picture of the first patient that was implanted, because when that patient was implanted and it came to the point where the cable should be connected to the implant, it turned out that there was at least 1 meter cable too much in some of that. And then they started to make loops on that to put them somewhere here in the chest area. That was a nightmare. And I said, now we understand what you asked us 3 months ago. Can we just cut them now? If a surgeon says just, then you have to be very awake immediately. No, it didn't work. That worked well with respect to the implantation. It didn't work very well in the first implantation because it turned out that there was a slight mistake in the electronics that led to some interferences. And that means if you wanted to power that system, the feet already moved. And then after 6 weeks, first of all, we had to find out what it was. Then the electronics had to be changed, and after, I guess, 3 months, the person was re-implanted with the electronics with less interference. And it worked very well, given the state of the art that we used. It didn't work very well, to be honest. So it was the best possible to that point of time, but it took so much effort for the person. He was a skinny guy, so that large, very skinny, like a marathon runner from the status. And after 6, 7 steps, he had a pulse of 220 beats per minute and was completely exhausted. So that means the whole and got fatigue. So that means it was nothing you could use in daily environment to have a nice walk on Sunday afternoons, whatever. So he was keen on getting that, and he was keen on being the first one getting that. And he made a lot of money out of his storytelling on the television in talk shows, published some books, and used that for about 15 years. And then said, it doesn't make any sense for me, and he got explanted after 15 years. But the good thing was all the technology worked on that. That was at least from the engineering side, and we didn't do too many mistakes. But from the physiology side, that always turned out that this idea of walking doesn't work well with that approach. I give you a homework. This is now the time where a lot of you wanted to leave over the Christmas break and party a little bit before, do some pub crawling and have fun in the city. Check out how many steps there are from the main bar area to the toilet. And I'm pretty sure you will not find more than 5 clubs or bars in this town where there's no step in between the bar area and the restroom area. either 2 steps above or restrooms are in the basement, whatever. That means if you would have something like that and you need to go to the restroom, you should be able to stand up and walk and climb 2, 3, 4 stairs. Then it would be really beneficial. Or standing up, lifting your hands and taking something from the upper shelf. But this is made such, and this is not a criticism of all the research, but it cannot be done better so far. People cannot lift their hands from a walking frame. You always need a walking frame for balance. You can do some steps or a harness, but a harness doesn't help you in your daily environment. There's no one behind you with a holder for the harness, and that means it's really tricky and tedious. There are kind of new approaches where colleagues of us from EPFL in Switzerland and Geneva are working on, where people go directly to the spinal cord. I told you something about central pattern generators in the lumbar area, and if you stimulate them, you can overcome that inverse recruitment. So you get the nerves in the right order, and you can overcome fatigue. So it's weight bearing, that stimulation, but it's not yet at a stage where persons can really walk without using a walking frame. So still some challenges for you and your future research if you want to go into that direction. For some applications, and this is mainly for diagnostic applications, there are intramuscular electrodes. So you go directly into the muscle. There have been some approaches that looked a bit like miniaturized fishing hooks in the US and in Japan, where braided wires were implanted into muscles with a kind of hooks at the front end that you get them in, but you cannot pull them out immediately. A lot of work has been done in the 1980s, also with percutaneous cables. At Case Western Reserve University in Cleveland, Ohio, in the US, after stroke for rehabilitation of the lower leg muscles. And later on, up to around 2000-ish, in Sendai in Japan, in rehabilitation hospitals. I was scared. I was there end of the 90s and got a lab tour, and in a rehab hospital they had persons really with 8 or 10 or 12 or 14 wires poking out of the skin, and I asked them, does that work, any signs of infection, whatever, and they put it all on, oh, this is a cultural thing, yeah, you're too soft in Europe, you know, we don't take care, we don't care here in Japan. Unfortunately, he was not that right. There were infections also in Japan after a certain period of time, and unfortunately, they had the government closed that rehab center there afterwards. Then I go back. Yeah, for the recording, the question was with respect to walking, are our biomechanical models good enough? Could that be a problem? I would say the biomechanical models are good enough. They're not perfect, but they're good enough. The problem and challenge is that we have us as human in bipedal walking as a system with too many degrees of freedom. Yeah, we have 2 wrists, 2 knees, 2 hips, And the trunk and the upper body is not one element, but with the arms and the head and whatever we have a multi-element model. And that would mean we have to control at least the wrist, the knee, and the hip in a way that the center of gravity of the rest of us stays over the feet. And you might have done that balancing a stick on your finger. That is hard enough. I mean, we can take machine learning, then it's easier. But imagine you would have not one, but 3 sticks being connected not just with a piano hinge, but with a multi-degree of freedom joint. And then you should balance them that they don't fall. And that is one of the challenges there, really, and that multi-joint system to keep the center of gravity over our feet. There are strategies, and you all know those strategies. If you have to stand for a longer time and you're getting tired, in those cases, at least I try to lock my knees and try to lock my hips. So if I lean back and the knees are in extended position and I stiffen my hips, I just need to balance myself over the ankle joints. And that is an easier control task than balancing myself with the knees and the hips and the rest. And this is a kind of answer to your question. You know, it's a really very complex control task that needs to be done where the patient can still move his or her upper trunk. And that will mean if you put that all into a machine to do that, you might have a co-adaptation between the machine and the patient. So 2 control systems in the worst case working against each other. Yeah, and I think that is one of the major challenges there to get that somehow solved. C4, C5 spinal cord injury. That means hand was paralyzed, no arm and shoulders were working. And the research paradigm was the question, can we reduce fatigue while minimizing the force during grasping? So that you don't grasp as hard as possible, but just as strong that you do not let your object fall. So, back to the intramuscular system. I want to close that shortly. Oops, now, here we go. Another intramuscular system that was covering each and every conference in rehab engineering and biomedical engineering for about 20 years or longer was the bionic neuron. That is still a clever approach where you have a coil, you have a small electronic circuit that does a kind of address decoding, 8-bit, so you have 256 options. You have 2 electrodes, one on each side, and you have inductive powering. So if you apply inductive power from the distance and you have that address selection, you can say, hey, implant number 2, it's you. And then this implant opens a switch and delivers then, after being powered, the stimulation pulse. With the idea that you can address several of those with one transmitting coil, having the energy and data that decodes which of the target implants should be addressed. This is a photograph, so it's really made out of glass. That was always a kind of argument. So is glass stable enough or is it brittle? Would it break if something happens? at the very end, those guys skipped the glass and went to ceramics. So, and then the discussion was off. The application was tested up to patients in stroke patients as sketched out here. So if you have stroke and hemiplegia, during that acute phase where you do not recover yet, the muscles are not activated and your shoulder hangs down without muscle support, stretching the capsule in the shoulder joint. And if you undergo rehab afterwards, you have that pre-damaged shoulder because your shoulder capsule is already a bit loose and baggy. And the idea was, can we implant those by a biopsy needle? Well, probably a larger biopsy needle, 3-4 millimeters in diameter, just inject it in the muscle. And then put a kind of long t-shirt above with a coil, and then you can power that. The idea was good, but it turned out with the first run series of those implants that the muscles were activated that well that those capsules moved inside the muscle. You know, if you're not exactly aligned to the muscle fibers and the muscle contracts, you have a kind of tilting force on that, and by that those implants tilted, and in the worst case they broke at the transition between the electrodes and the wires. Shown here on the edges, the electrodes are connected via wire through that glass pearl as an hermetic seal to the implant, and it broke here. If you remember vaguely your micromechanics, and your mechanics and a bending beam, then you would have maximum force at those transitions there. And that was a showstopper. They had to change that. They improved that, and I'll tell you the real showstopper at the end of that. The second application was incontinence, with the idea, and they said, well, incontinence is something where you should have probably a battery and not just a coil, so they integrated a very small battery. And while sitting on your toilet seat, this battery could be recharged because there was a coil wrapped into the toilet seat. And if you sit on the toilet seat, you're in the center with your sphincter of the urinary bladder of that coil. Beautiful idea. They didn't measure the temperature. And by powering the implants, the study participants all complained that they don't feel very comfortable sitting on such a hot toilet seat. That was something which I cannot forget any longer, because that was such a lively presentation on that conference. But the real showstopper, and then it vanished from the market. So it was all where I said, well, this is very close. And they never went to the market. And the showstopper was, and that was published years after that in the IEEE journal, as a kind of more life story than a scientific publication, that they chose the wrong frequency for powering their implants. I was in a US institute, and they unfortunately chose a frequency that was reserved for the US military. And they were not happy at all, the US military, and there were lawsuits and negotiations, and that span over 10 years. And that means they just missed that. And that broke their neck, because all the developments, all the tests that they already did for the approval were done with that frequency, that specific absorption rate, everything. And therefore, my recommendation for myself and for you, always check the frequencies. There was another development, which I do not present here in that context, from a New York institute. They chose a frequency that is used for sports events. That means when the New York Marathon is, or the Tour de France, you're not able to use your implant, because this is then switched for broadcasting. That sounds completely stupid, I know, but it's sometimes that you you check where frequency bands are in general, and you don't check if they're really used or not. And after those things and those stories, there has been an harmonization of standards, and certain bandwidths are now reserved, but not for medical devices exclusively, but also for other applications. And that means we all have to check that we are in the right range, that this is not too busy, that bandwidth, that we can use that in short-term ranges, whatever, that this part is safe, and one should do that at the very beginning. Otherwise, you cannot use all the data that you collect in the research phase when it comes to the transition phase and into the translation into a product. One thing that is no longer on the market, and one thing that is on the market, and one thing that is not on here but looks similar. These things all come from the 60s, 70s, where electronics components were still packaged in metal cases or glass packages. A metal case or a glass package is hermetic. That's beautiful. You save your content by that, that no water or no ions can reach that. And then you can take those few components and can encapsulate them into silicone rubber. And if you do it right, it lasts forever. That doesn't work if you try to cast your 6 nanometer CMOS chip, latest generation, and put a drop on silicone rubber on that doesn't work. But if there's a glass package around or a metal can around, then you can take your old style bipolar transistor, 2 diodes and a capacitor on a printed circuit board. In this case, it's aluminum ceramic with screen printed conductors. You solder it, you put silicone rubber around after cleaning it thoroughly, and then it lasts forever. It will be very hard to bring that through current legal frameworks of approval documents, but there is a kind of grandfather agreement that things that have been approved in the 1970s can still be used if you do not change anything. I'm pretty sure that this regulation will be cut shortly. So, and then you have to reevaluate everything. With respect to the electrodes, there have been some applications with epineural electrodes because micromachining was not yet around in those days, and they took thin wires, curled them together and twisted them, and then used surgical material and sutured that on the target nerves. That sounds a bit odd, but worked very well, especially in the phrenic nerve, to innervate the diaphragm in persons having a very high spinal cord injury, so C3. That means your brain is still working well, but your ventilation doesn't work at all. And normal therapy is overpressure, insufflation, so you get intubated or you get a tracheostomy and get ventilated by that. And 50 years ago, even 40 years ago, those ventilation machines were really heavy and large. Nowadays, they shrunk down. They can be carried on a wheelchair, and therefore those phrenic pacemakers that stimulate the diaphragm are no longer that much on the market. Due to some changes in legislation, one company went into bankruptcy, one company gave up at the new legislation, and there is one company around in Finland, Atrotech, who are still manufacturing those devices on demand. One of the electrodes that, for my impression, looked very stupid, but is now one of the electrodes in vagus nerve stimulators, is an helix electrode. It goes around the nerve, and in early days materials were relatively thick, and if you took a massive material and wrapped it around the nerve. It was so massive that the nerve died. And therefore, those guys said, well, why not take an open spiral with the advantage that the contact area on the nerve is smaller. It's like a spiral, so it can go a bit larger and grow smaller, follow the movements. Works quite well. Its disadvantage, it's monopolar. It's just one contact. It's a kind of open structure. That means you cannot use ideas of how to concentrate the electric field or whatever, just that contact versus a counter contact to close the electrical circuit there. In the vagus nerve stimulator from Cyberonics, now called LivaNova, after changing their names, it's implanted more than don't know how many 100 times worldwide, and works well. But it's an on-off stimulation, so there's no spatial selectivity. You either stimulate the nerve or you don't stimulate the nerve, and you stimulate everything that's on your way. The idea then of putting something around the nerve really grew and fertilized a lot of research groups from the 1970s on. As said, the first devices were really massive, and they got a lot of fundamental work has been done in the 80s, 90s on that. With the idea, if we have an insulating shell, let's say, around the nerve, we can concentrate the electric field such that we keep it inside that cuff, and having more electrodes, we can also selectively activate certain parts of that nerve. We always come from the surface, but we can come, let's say, from 1 o'clock, from 3 o'clock, from 6 o'clock, depending how many contacts we have, and keep the electrical field inside by having a cathode in the middle and anodes at the outer side. I will rush over all the miracles of those electrodes because I like to focus on that when we have a lecture on selectivity. Therefore, it's here just, hey, they are cuff electrodes, they are wrapped around the nerve. That means the nerve stays intact, and we don't have to play around with the nerve. So no poking, no opening, no nothing. It's just wrapped around the nerve. The problem, as you can imagine, if I want to selectively activate fibers that are not on the surface but in the middle, I come to limitations because normally I would activate all the surface fibers before I get those in the middle. But I think you always have to pay a price, right? If it works, this is one option that now goes into clinical applications. It took a while. That's only 40 years or something like that, but now it's going towards clinical applications. Yeah. The insulator of the cuff electrodes, it's mainly silicone rubber. So you can do that with precision mechanics or laser structuring. And the beauty with silicone rubber is that you can stretch it. Yeah? And if you have one piece, let's say one sheet, and you activate it or do some magic glue on that, and you stretch another shield and glue it to the first one, and then you release it, then it shortens again, and it's like a bimetal rod. If one shortens, it curls up. That means it makes automatically a spiral. And that is one of the applications, the spiral cuffs. The alternative would be take a silicone tube and cut a slit into that, and then you can open it and close it again. And this mechanism is beautiful, especially the spiral cuff, but it comes with challenges when you consider the variability of humans. means if I look deeply in your eyes, I don't know how large the diameter of your nerve is, right? And that varies in the peroneal nerve that goes over the knee. And there was one application for stroke patients from Neurodan, where a cuff electrode was placed around that peroneal nerve at the knee. They always needed to have cuff electrode diameters between 1 millimeter and 1.6 millimeters in stages of 0.1 millimeter. That means you don't know that. You need a whole battery in the surgical theater looking how does my patient look like and then select the right one. That is a bit challenging because from the company side and the surgical side, but if you do it in a clever manner, you can succeed with that. And there was a paradigm like a holy grail. You're not allowed to squeeze a nerve, otherwise the nerve would die. You remember probably that table that I shared with you about nerve damage. And the first degree of nerve damage was if you squeeze the nerve, we have dropouts in functionality. And then one of my favorite colleagues came up to stage and said, I have a new electrode, I just squeezed the nerve. I said, hey, come on, you know it better, don't you? And then he admitted after some beers that he cheated a little bit with his first study because, well, he cheated in the way that he selected a nerve that was not perfectly round but already flat. So that means his flat electrode already matched well around that nerve. But he said, well, we have to take care of what we are talking about. It's not about squeezing the nerve fibers, but we have certain fascicles that are arranged in a very loose tissue. And if I do that slowly, they have enough time to rearrange in that connective tissue, and then they place a kind of one next to the other. And by that I get at least fascicle selectivity. And he did that from simulation studies over animal experiments up to the first humans. And I forgot to put the reference here. And it worked well. Still the thing, this is for nerves with a lot of fibrous tissue, so with a loose epineurium where those fascicles can arrange. In the same time, people came up and said, well, this is not selective enough for me. I want to have something which is selective on the level inside the fascicles, or at least the fascicles. And the first thing that was done there was the idea, well, if I have a hand surgeon who is very skilled, the hand surgeon should be able to use needle and a surgical thread and pull something exactly into that fascicle. And if I exchange the surgical thread by an insulated wire and leave it in, and this wire has a contact space, I should be able to stimulate that. That was the idea of the longitudinal intrafascicular electrode, the LIFE. And that was done here with Kevlar, with metal, with insulator. And the early things were really fascinating. That was a really brave, straightforward US colleague of mine, and he went after some months into humans directly. and did some the first sensory feedback studies with that I guess it was in the 1990s, got some good results, and then went to some other applications. But that idea was really going through many research groups, and I was involved in one of those where I said, well, if you need one needle or one filament per nerve fascicle, that's really annoying. If I have 5 or 6 of them, it's an endless surgical procedure. Why should we go longitudinal through that? Why can't we go transversely through that? and then cover all of them, take micromachining and put a lot of electrodes on there. And if we are lucky, they all look in different fascicles, and then we can stimulate multiple fascicles with one implant. So that was the birth of the time electrode in 2007, 8 or something like that. And we tested a lot, and in 2002 it went into the first human to deliver sensory feedback after amputation. And I promised to give a lecture on sensory feedback at the very end, but I thought I should include it here because it's peripheral nerve stimulation. Yeah, that's a micromachined system, a thin foil that is pulled with a needle and a surgical thread through the peripheral nerve. And you can't see it here because it's so small. What you see in the lower picture is that the cables are relatively massive, and the part that is important is that part that you can hardly see here. That is the microsystem made out of a 10 micrometer thick foil that is placed in there. The question is, how stable is that? And we made experiments, and the usual thing in medicine is to use Kaplan-Meier plots. Means you have the weeks or the days or the years on the x-axis. And in a standard Kaplan-Meier plot, you have the survival rate of the patients on the y-axis. And that shows you, if you have a therapy, how good your therapy is compared to no therapy, especially in oncology, so if you treat cancer patients. And we thought we can probably take that Kaplan-Meier plot to look how well our electrodes perform. And I like to point you on the right-hand side. The left-hand side is more for experts in the field that want to discuss details. Right-hand side, each line, each color represents one patient. 100% right-hand side scale bar on the y-axis. For the others who wonder what left-hand side is the electrical impedance of the electrodes. And we decided that the threshold above 150 kilo ohms means the electrode is no longer working due to the voltage swing of the simulator that we have. We could not drive more than 150 kilo ohms. Right-hand side was then, does the patient feel something? Yeah, and we said if the patient says, I feel something, it's intact. If the patient says, I have no idea what you're talking about, that's fail. Yeah, starting from the first day on, when we had number of contacts and the patient, oh, that's all fine. Next week, another questionnaire. And then it turned out in 2 patients, they have been implanted with 1 or 2 weeks difference, that a lot of electrodes failed. And we were completely sad and got then the feedback that unfortunately, the patient broke the connector and the wires were no longer connected to the connector. And we said, how can that work? Yeah, the patient did it by one hand. We said, we told you at least 3 times you should take both hands, and the patient is not allowed to pull on the cable, but you should connect the whole system over the plug. And then we had some time to fix that bug. And the 3rd patient was implanted, and having the red line there, first 10 weeks are already influenced by the foreign body reaction. Therefore, electrodes can drop out and come back, whatever. But it turned out that it remained stable to the very end of 4 months here. And afterwards, and this is something for you as engineers, what I want to share, how can you assess that something is good? As shown, you can either measure an electrical parameter and say, this is my predictor. If I want to push current through, I measure the voltage, and then I divide one through the other and get an impedance. And if this is in a certain range, I call this working. If it is above, there could be a hint towards some failure. Or you ask the patient, does this thing work? Do you feel something? But as a scientist, you want to know what's really happening there at the spot, right? You want to understand the mechanisms to make a device better. And we asked to get our electrodes back after the termination of the experiments. That means the patients got explanted afterwards. That was necessary because we were working with percutaneous wires. So wires were poking out and you cannot leave them in. They are an entry path for germs and infections. And then we got a lot of bits and pieces, and afterwards the surgeon said, you know, I want to save the nerve of the patient, not your electrode. So they cut everything what they could cut. That means we got back a lot of little pieces and had to make our mind, what does that mean, what we see? And first of all, we had the impression that we see a lot of scratches made by scalpels and tweezers during the explantation procedure. And that might have happened because that integration into the scar tissue was so tight that it took some force to get the things out. We did a kind of analysis, so we counted electrodes, how many did we get, how many were implanted, how many contacts were intact on the last day, and how many intact contacts do we see now. And we found out that there was a gap in between. So a lot of contacts seem to be damaged during the explantation procedure for reasons that we're still looking at. That means it could be that you have a lot of tissue integration there, and when you pull, that the force between the tissue and your electrode metal is higher than the force between the electrode metal and the substrate where it is on. Things like that. I have no clue. We're still developing methods to investigate that and analyzing those contacts to see what the root causes of that failure were. But I want to share that with you to give you an insight what research means in that context from the engineering side. And we, of course, checked the cables using here computed tomography on a material scanner and found what we thought that we see, that all the wires broke here in the transition. That is a mechanism you know very well if you're lazy and your computer is somewhere in the power socket and you take the end of your cable and pull it out. Pulling out is one thing. Imagine you would try to get that into the power socket just by pushing somewhere, right? That's even worse. And that's what they did in the rehab center. They did not take the connectors, but really pulled and pushed on the cable exactly here. And that means you have a lot of forces there. And we did not anticipate that because it was so easy. After knowing that, we just put a lot of silicone rubber and more tubing around, and it was problem fixed. Yeah, and we made our mind about so many things, but not about those 2 centimeters there. Yeah, and then I'm coming to an end. We analyzed all those contacts, and as you might see or might agree on the lower left, the SEM pictures, that looks like somebody had a pair of tweezers or a scalpel and just, oops, was there something? Just scratched over the electrodes. This is shown here in different light microscopy with polarization filter, white light interferometry, and SEM. So we've seen damage by mechanical handling or by handling and mechanical interference. We see really pristine electrodes and some crests that might come from material changes and intrinsic stress in the thin film. That is where we still want to dive deeper into material analysis to find out what this really is. And we are lucky that we have a brand new toy in our laboratories with material analysis options, and currently now looking at that. TOF-SIMS is one of the time-of-flight secondary ion mass spectroscopy. You can grind layer by layer from those devices, and the residues fly into a mass spectrometer, and then you get an idea if there's, for example, more sodium or more chlorine in your platinum or iridium oxide as should be. And this gives you a hint about the material composition and if materials change in the present or in the body. And another thing, and then nearly at the end, was that some contacts were perfectly working at the beginning and dropped out after some weeks. And we wondered what happened there. Are they gone completely? Are they damaged? And colleagues of us did a simulation study. If you have an electrode, if you have the device being passed through a vesicle, and you're inside the vesicle, and you get scarring tissue around, the electrical field changes due to different resistivities and permeabilities, but you still guide your current through that nerve vesicle. Then you still get the same activation. However, on the right-hand side, if your electrode is in between two vesicles, that might address two different places of the foot sole here in lower limb amputation, and you get scarring around that, probably one contact that was previously activated first gets insulated, and you reach the other contact first while increasing your amplitude, and thereby you get different perception due to that scarring behavior of the electrodes. That means you really have to look in a multifaceted way on that whole analysis to get a clue why your performance is as it is. So what else has been around? One option still under investigation is the idea to shoot a bed of nails also into peripheral nerves. The first one who did that was Kevin Warwick, professor of cybernetics in the University of Reading in the UK. And he wrote a book called iCyborg. And he claimed to be the first cyborg on Earth because he had some information technology gadgets on his body or in his body. And he did an experiment or a study where he ordered one of those arrays and let it implanted into his lower arm to record signals and drive the colors of a necklace of his wife. So depending on his mood, the necklace either was pinkish or bluish. This is definitely a book I would not take on an island if I have to take 3 things with me. I tried to read it twice or 3 times, I always ended at page 100 something, so it's not that good. But he showed that it works, that you can put something like this into your peripheral nerves without any harm. But I'm not very convinced about the approach because of a lot of relative movements between silicon-based implant and peripheral nerve in the periphery. And last not least, I would say my favorite one because that saved my PhD thesis. That thing, and unfortunately I was the first one to be able, with my development, to let others find out that this is a completely stupid approach and that it doesn't work. That's not that nice if you find out that something doesn't work. So the idea of sieve electrodes is relatively old for amputation traumata, and the idea is why not, if the arm and the nerve is cut, can I put something on the cross section where the nerve fibers are, and by whatever kind of modulation or just waiting, the nerve fibers might sprout out. They are captured into microstructure with electrodes, and then I can record or stimulate or both. And I would have a perfect interface to drive a bidirectional hand prosthesis or leg prosthesis or whatever. Beautiful idea. There are many challenges. One challenge was in those days to get cables on that. That did not work well on silicon, and that was an idea, why not taking polymers and integrate thin film cables into that, to integrate a lot of electrodes as shown in the upper right and let nerves grow through, which is shown in the lower right from a rat model. And the whole thing stopped after 6-7 years of research because physiologists found out that sensory and motor fibers that are arranged in fascicles before trauma and have kind of split, this part is sensory, this is motor, look like a salt and pepper pattern at the very end. That means you have no longer any really anatomical organization of that, but everything is mixed up. That means you have no idea where to stimulate and what to do. And the sensory fibers are much faster than the motor fibers. So when you cut the nerve and you wait, the holes are covered by more than 80% of sensory fibers before the first motor fiber arrives. And that means that there is a mismatch between motor fibers and sensory fibers, and together with that salt and pepper arrangement of everything everywhere, was a kind of death sentence for that approach. Some nice words in the outlook of that paper. You can do additional biotechnology and integrate nerve growth factors that guide sensory nerve fibers to the left and motor fibers to the right and whatever. But it turned out that this is probably not the best idea. And in parallel to that, higher channel cuff electrodes, the live electrodes, the time electrodes arose and showed that there are less invasive approaches that have even better performance. And with that, I like to close for today. We have covered not all, but a lot of approaches on the peripheral nervous system. And I thought it would be good to give you some kind of failure analysis at the end with recent research on that. The last paper of that simulation stuff has been published about 6 weeks ago. So it's really brand new on that. And I promise you next week, central nervous system, we start in the early ages, close to the Stone Age approach, and then we end up with something that is even not yet published. So we're currently latest results there on compatibility and performance. With that, I'm at the very end. Thank you very much for being here. I'm looking forward to seeing you again next week. Bye-bye.